Right. That obviously is not true. This is Physics 253, a course in relativistic quantum mechanics. My name is Sidney Coleman. The apparatus you see around here is part of a CIA surveillance project. I fall within their domain because I read JATP letters. No, it's part of an experiment which may reveal itself to be a failure if that machine begins to make noise that disturbs some of you. If it does, tell me and I'll have it turned off. I suppose I should begin by making some remarks about the way this course will be administered. I will hand out, after the course is going, sometime during the second week, a problem set, and I will continue handing out problem sets at regular intervals. The problem sets will be graded by John Losecco. John, stand up so people know what you look like, if they don't already. And if you have any questions about the way your problems are graded, John is the one to consult with. If you have any questions about the lectures, ask them during the lectures preferably, or if you're shy, come to see me. I am around practically every afternoon. My office is Lyman 333. And my phone number is my office phone is 53763. If I am busy, I will tell you I am busy and send you away. If I send you away several times in a row, it is your responsibility to get mad and remind me that I sent you away several times in a row. The grading will be based on the problems and on a 2 or 3 day take-home final exam, which you will get at the end of reading period. If you do better on the exam than you did on the problems, the grade will be based on the exam alone. If you did better on the problems, a weighted average will be taken. That's all of that. The official text, that is the book you're required to buy, according to the signs in the coupe, is, it's the only way to get them to buy enough copies, is Bjorkane and Drell, 2-volume set. I will not use it as a text. My way of organizing this material is very different from the way chosen by Bjorkane and Drell. However, I will try and keep my notational normalization conventions close to those of Bjorkane and Drell, and it is a very good book in the sense that it contains very few false statements and contains many worked out computations and other interesting things, and is, although, well, I shouldn't say it's a very good book, but it's the best available, and you certainly will need a copy as a reference. People like it. By an objective test, it is the book most frequently stolen from the physics research library. Okay. Now, I guess that's all the preliminary material unless someone has questions. The subject of this course is relativistic quantum mechanics, and this is a subject that has a notorious reputation for difficulty, and indeed as this course progresses you will see this reputation is well deserved. And the first question that I should address before I get into any technical details is, why is it difficult? After all, if we're doing two-particle scattering in ordinary quantum mechanics, scattering in a rotationally invariant problem for a spherically symmetric potential is considerably simpler than scattering in a general potential. In general, whenever we pose a symmetry or invariance requirement, we simplify things. We look at a special case rather than the general case. We make things less complicated rather than more complicated. Why is it that when we impose the condition of Lorentz invariance, things get more complicated rather than less complicated? Why is it that scattering in a Lorentz invariant potential is not even simpler than scattering in a spherically symmetric, a rotationally invariant potential? Well, the reason becomes clear if we think try and think realistically about any process in which relativity is going to be important. Let's suppose we consider, just to take a definite example, pi plus pi minus scattering. We would expect relativity to be important when the energy, the kinetic energy, say, of one of the pions, viewed in the center of mass frame, is on the order of or greater than mc squared, where m is the pion mass. On the other hand, this is a domain where the purely kinematic corrections due to relativity become so large that they cannot be ignored. On the other hand, this is also the domain where the energy of the pions is sufficiently great so that this process is also possible. That is to say, the energies where relativity is important are also the energies where pair production is important. And therefore, there is no point in the world as we know it, and we will later see even in any world we can reasonably conceive of taking account of relativity without simultaneously taking account of pair production. That is to say, if we're doing relativistic quantum mechanics, the two-body problem is inextricably, at least inextricably at first glance, mixed up with the four-body problem, which is in turn inextricably mixed up with the six-body problem, etc. So although we have much more invariance than we have in non-relativistic quantum mechanics. To be precise, we have 3 extra symmetries associated with the 3 Lorentz boosts in various directions. We also have much more degrees of freedom to deal with. We can't look at a 2-particle system, a 4-particle system, a 6-particle system. We've got to look at them all at once. And what we lose in having many more degrees of freedom to deal with more than compensates for what we gain by having more symmetries. And that's why the subject is complicated. You might think the argument here is a little bit too crude because I have talked about an energy where relativity is not only important, it is overwhelmingly important. And I could imagine I was working in a smaller energy domain where relativity is 1% or relativistic kinematics a 1% or a 1,000th of 1% effect, and then I would be very much below production threshold. And you might think that in that case I could sensibly talk about a 2-body system without worrying about the 4-body system. This is in fact not the case. Suppose I were, for example, computing the corrections to an atomic energy level. Well, we all know how perturbation theory goes. We have a formula for the shift in the energy level. There's a first-order shift, and then there's something like if n is the state we're studying, and v is the interaction, sum on m, en minus em, plus other terms. Now, m is supposed to be every state in the world. In particular, it could include states that include the same pairs that gave us trouble in the actual production processes. What suppresses the pair states, what makes it possible for the computations in non-relativistic quantum mechanics, which take no account of pair states, to work to such accuracy, is the fact that, of course, if we're looking at a low-lying energy level in an atomic system, this energy denominator is enormous. Indeed, the effects of the pair states are suppressed by a factor are on the order of some characteristic atomic energy in the atomic system. This is a very crude order of magnitude computation over mc squared. Perhaps you'd like to write 2mc squared, whatever, the energy required to make a pair, the thing that makes this denominator enormous, and this is what it's got to be enormous with respect to. Now, this is indeed a small number, but unfortunately it is exactly the same small number that would come in to the purely kinematic effects, the departure of the kinetic energy from its non-relativistic form due to the effects of relativity. So once again, even when relativistic effects are small, the kinematic effects of relativity are precisely the same order of magnitude as the effects of pair states, and we have no business dealing with a system of only two bodies, or one body and a potential. These remarks are rather preliminary and crude order of magnitude, as you see by these wiggly lines I make, rather than the equalities, but I think they express the essential point. I should say that what I am saying is a generic statement. There are very special cases where, because of the details of the dynamics, the kinematic effects of relativity are larger than, considerably larger than the effects of pair states. Among them, unfortunately, is the hydrogen atom. And that's why Dirac's theory of the hydrogen atom, which did not include the effects of pairs, was so successful. That was a good thing because it told people that the basic ideas were right, but it was a bad thing because it led people to spend a lot of time worrying about one body and one particle and two particle and three particle theories, because they didn't realize the hydrogen atom was a very special system. So much for preliminary remarks. I will now go to the dullest part of the lecture, in which I will set up my notational conventions and the conventions I will use for dealing with special relativity and things of that kind. It will be both the dullest and the most obscure, because I will try and go through these things very fast, since I presume 90% of you have seen 90% of the things I'm going to say. And thus, you will be bored 90% of the time, and the other 10% of the time you will be baffled, because I will be going so fast. But since it's a different 90% and a different 10% for each member of the audience, there's no other way to organize it. It's getting a bit warm in here. Oh, I should say, are there any questions about the preliminary remarks, about the order of magnitude discussion and so on? Now, firstly, units. That's simple. Since the subject is relativistic quantum mechanics, every formula we have will involve a C and an H bar, and therefore I will set them both equal to 1. This leaves us one unit free, which I will keep free. Typically, we will choose it in a given problem to be the mass of the part of an interesting particle in the problem, which we will then set equal to 1. So remember, we are always going to be using units where the speed of light is 1 and Planck's constant is 1, and we'll never get into any problems. What's that? Just remember that an ordinary macroscopic motion, like this, for example, has infinitesimal velocity and astronomical angular momentum. No. Relativity conventions. Classical relativity. Special relativity. The arena for all the physics we are going to do is the arena of ordinary special relativity, flat space-time, in which is a bunch of points labeled by 4 coordinates, which we write this way, x mu, where mu is 0, 1, 2, and 3. X mu will sometimes be written separately, separating out the 0 component and the space component. And the 0 component is, of course, also called the time. Sometimes I will suppress the index when there's no possibility of confusion and just write this object as x. X mu is not the only 4-component object we have to deal with. For example, in classical physics, there is a momentum of a particle, which I can call p mu, write as p0p, and there the 4th component the time component has a special name. It is called the energy, and the space component is, of course, called the momentum, and sometimes I'll write this as p. Since we're doing quantum mechanics with h bar equal to 1, I can indiscriminately write p as k, and I will sometimes call it p and sometimes call it k. I can't remember. And then I will call the time component omega, the frequency. The primary objects of interest in relativity are so-called four vectors, four index objects, just like x and p. And they have between them, if A and B are two such four vectors, an inner product, which I will denote as A dot B. This is A0, B0 minus dot product A dot B. This is a so-called Lorentz invariant inner product. This thing can also be written as sum on mu and nu, G mu nu, A mu, B nu, where G mu nu is defined by G0, 0 equals 1, equals minus G1, 1 equals minus G2, 2 equals minus G3, 3. G mu nu is called the metric tensor. We will adopt the so-called Einstein summation convention, I presume familiar to most of you, where sums over repeated indices are implied, and therefore we will also write this expression as G mu nu, A mu, B nu. Any questions so far? Please note I have adopted the signature. Of course, any multiple of this thing is also a Lorentz invariant inner product. There are only two. Nobody uses a convention where this is multiplied by the square root of 2 or something like that. But many people use a convention with minus the metric tensor that I have used. This is the mainly minus convention, 3 minus signs and 1 plus sign. I will stick to it throughout. It is convenient frequently to define an operation of lowering indices. A lower nu equals G mu nu A upper mu. Of course, working this out, this is just matrix multiplication of a vector by a matrix. A lower 0 is A upper 0, and A lower I is minus A upper I, where I equals 1, 2, and 3. In general, I will use Latin indices for the space indices and Greek indices where the indices run over all 4 components in space and time. Thus, another way of writing our inner product is A dot B equals A nu, B nu, or indiscriminately A lower nu, B upper nu. Since we have an operation of lowering indices, it is convenient to have an operation of raising indices also. We define the metric tensor with upper indices to be the inverse matrix to the metric tensor with lower indices. Have I done that right? No, I've done it wrong. It should be a mu. Where delta is the conventional Kronecker delta, equals 1, mu equals nu, 0, mu not equal to nu. Boy, is this dull. G mu, this is an easy equation to solve. This just says find the inverse matrix of the metric tensor. The metric tensor is a diagonal matrix with entries +1 and -1, and therefore in terms of our conventions, G upper mu nu is numerically equal to G lower mu nu. This is special to our conventions. If we hadn't set the speed of light equal to 1, the 0, 0 component of G would have had a c squared in it, and then the 0, 0 component of the other object would have had a 1 over c squared in it. Okay. Lorentz transformations. Lorentz transformations are labeled by a 4 by 4 matrix, which we will call capital lambda. They act on these 4 vectors in the following way. This is a kind of equation I will write down frequently. You may not have seen it. It says that under the Lorentz transformation labeled by lambda, the 4 vector A mu is transformed into the 4 vector lambda mu nu A nu. We could equivalently, of course, write this suppressing all indices just as straight matrix multiplication. A goes into lambda A. This defines, of course, a general linear transformation. We will be particularly interested in Lorentz transformations are transformations that preserve the inner product. That is to say, such that given any AB, lambda B equals AB. Whoops, and I wrote the inner product in a bad way, which is not the way I want to write it. That's the way I want to write an inner product in Hilbert space sometime. Lambda A dot lambda B equals A dot B, excuse me. I'm going very fast. If anyone is confused, anyone at all, please ask. It's silly to get confused by things as simple as this. Okay, everyone understands. Everyone has probably seen it all before. The Lorentz transformations form a group of transformations in the mathematical sense. The product of any two Lorentz transformations is a Lorentz transformation. The inverse of a Lorentz transformation is a Lorentz transformation, etc. This group has a name. It is called, tell you the name, O31. O stands for orthogonal group. This is pretty much like the group of rotations, except that there are 4 dimensions rather than 3, and there are the 3 entries that have a minus sign rather than all the entries having the same sign. ON is the orthogonal group on n real variables, orthogonal transformations. The 3, 1 means that it's not quite an orthogonal group because 3 of the things have one sign and 1 of them have another sign. Standard notation. You see it a lot in the literature. I might as well tell you what it is. This group is a bit too big for our purposes because it includes things that, in fact, are not invariances of nature, if we're very precise. Although we normally say things like the world is Lorentz invariant, it includes things like parity and time reversal, which, as you probably know, are broken by the weak interactions, if you've been reading the Scientific American. And therefore, we will restrict ourselves in this course exclusively to the connected part of this group. That is to say, only those Lorentz transformations that can be obtained from the identity by continuous changes. And thus we exclude things like parity and time reversal. And we will talk, when I say Lorentz group, I will always mean the connected Lorentz group. Mathematicians call this thing SO3 of 1, the S meaning specialized, the connected things. The corresponding thing, if we were talking about real rotations, would be to look not at orthogonal transformations, but rotations in the proper sense, excluding reflections. Under the action of the Lorentz group, vectors fall into various classes, time-like, space-like, and null, but I presume if there is a person in this room who does not know what a time-like, space-like, or null vector is, raise his hand, his or her hand, without shame. I went bananas on pedagogy when I was writing this up, and I wrote down the definition of time-like, space-like, and null. Anyone who doesn't know what those words mean? No shame. I'll close my eyes, you just cry out. Okay, I'll skip that part. Actually, the world is supposed to be invariant under a larger, though no more glamorous group than the Lorentz group. It's not only homogeneous Lorentz transformations, but space-time translations are supposed to be invariance of the world. Nobody got excited about that because that was known in Newton's time. But nevertheless, we will sometimes have occasion to consider this larger group that acts on space-time. It's labeled by lambda, a Lorentz matrix, and A, a 4 vector, A arbitrary. And it acts on space-time points by spatially translating and Lorentz transforming. And this thing has a name. It is called the Poincare group. So much for the preliminary discussion of relativity, which of course is not a complete discussion, but just to tell you some of the words and some of the notational conventions I will be using. Now I have a few more notational conventions, alas, which I have to describe before I can get into the body of the lecture. These are the conventions I will use for differentiation and integration. The fundamental operator involved is derivative operator, which I will call d mu, and is defined to be d by dx mu. Its time component is d naught. Its space component is the ordinary gradient, or it could also be written as d by dt grad. It acts on functions of space and time, of course. Note that I have written this with a lower index where I have written x with an upper index. This is correct. This does not transform like one of these objects. Where's the transformation? But rather like one of these objects defined somewhere. Whoops, didn't I define the... A nu is defined somewhere. Ah, yes, like one of these objects. And the easy way to remember that that is so is just to remind yourself that d mu x nu is delta mu nu by definition. If I wrote them both with lower indices, I should have a g on the right-hand side, and indeed that's what I would get if I lowered the x or raised the lowered the nu or raised the mu. An important object, almost as important as the Laplace operator in 3 dimensions, is the D'Alembert operator. The del squared, which we will write box squared, it is d mu, and is d0 squared minus grad squared. It is a Lorentz invariant differential operator. So much for differentiation. Now for integration. I will write integral d4x, meaning integral from minus infinity to infinity, dx0, dx1, dx2, dx3. Whenever I don't put any upper and lower numbers on a integration symbol, I mean that is to be integral is to run from minus infinity to infinity. The 4-dimensional delta function, I presume you all know what delta functions are. I will denote by putting a 4 on it. And of course, it obeys this equation. Occasionally, I will have to do 3-dimensional integrals, frequently. And then I'll have to talk about 3-dimensional delta functions. For example, in terms of this notation, Fourier's theorem looks like this. If we define the Fourier transform f twiddle of k of a function of x as integral d4x f of x EVI k dot x, k and x are both 4 vectors, then f of x equals integral d4k over 2 pi to the 4th f twiddle of k e to the minus I k dot x. Any other notational conventions? Yeah, in addition to the delta function, I will occasionally use the theta function. The theta function is defined by, it's a function of a single variable called a z. Theta of z equals 1, z greater than 0, equals 0, z less than 0. What its value is at z equals 0 at the jump is going to be irrelevant. In every place we'll use the theta function. The derivative of the theta function is the delta function, etc., etc. I'm getting bored, so I'm stopping this. Anyone has any questions about any of this? Anyone who is not in the position of having understood 90% of it before I put it on the board? Everyone is totally happy, ecstatic. Okay?
Will you be sticking to that for your handle convention?
I will try to, but there will be cases where I will not be able to. Yes, in general, I will try and adopt a convention where every every decay has a 1 over 2 pi associated with it. This will help us take care of the central practical problem of doing calculations in relativistic quantum mechanics, keeping track of the 2 pi's. Okay. This will unfortunately lead me at some stages to writing down equations with square roots of 2 pi's in them at intermediate stages, but I will always be cunningly, craftily arrange matters so that at the end, when we get our final formulas, every decay will carry a 2 pi, and there will be no other place a 2 pi comes from. That's important. One of the most important things in this subject is keeping track of the 2 pi's. I mean, it's serious. If you're going to do physics and you invent a beautiful theory and someone says, is the experiment doable, to check your theory, and you do a little calculation and you say, yes, it is, and then they spend $1.5 million to do the experiment and they can't find it, and then you go look at it again, you discovered you've put a 2 pi squared in the numerator when you should have put it in the denominator. You feel pretty silly, okay? Keeping track of the 2 pi's is of critical importance. Now, okay. We are now ready to investigate our very first example of a relativistic quantum system. It will consist of a single non-interacting structureless particle in infinite space. It's better be a single particle. It better be non-interacting if I'm going to restrict myself to a single particle, as we said, in accordance with our previous remarks. Because the particle is structureless, it has no spin, nor does it have any internal excitations, then the Hilbert space of the theory is spanned by a set of basis states, which we will choose to be momentum eigenstates. I will label them by a vector p, and the momentum operator, capital P, acting on these. I will normalize these states for the moment in the conventional way of non-relativistic quantum mechanics. P prime P equals delta cubed of P minus P prime. That describes the Hilbert space of states on which my theory acts, which constitutes my theory, all linear superpositions of these things. To determine the dynamics, I have to give the Hamiltonian. Well, we all know enough relativity to know what the Hamiltonian is for a free particle. The energy of a momentum eigenstate is square root of P squared plus mu squared. We will have occasion to refer to this expression many times, so I will call it omega sub P, acting on P, and mu is, of course, the mass of the particle. This completes the description of the system. That's all there is to it. But now, of course, we're going to investigate the system in more detail and try and get some information from it which we can later use for generalization to more complicated systems. But by the standard rules of non-relativistic quantum mechanics, I have totally described this system. I have told you what the states are, and I've told you what the Hamiltonian is, and that's all there is to it. Any questions? However, I've also told you something that you might question. I said this is a relativistically invariant system. What the devil do I mean by that? In what sense is this relativistically invariant, or anything invariant, in fact? What does it mean when we say a system is invariant under the Poincare group, or under the rotation group, or the group of spatial translations, or whatever? Well, let's, for definiteness, focus our attention on the rotation group. I presume you all know the answer to this question from previous physics courses you've had, but let me at least phrase it in my language. What is rotational invariance? Well, first we have to know what a rotation is, and we all know that from classical mechanics, if no place else. A rotation is a 3x3 rotation matrix, R. We want to say we apply a rotation to a quantum mechanical state. We rotate it. Well, we certainly don't directly apply this 3x3 matrix R to a quantum mechanical state, because that doesn't make any sense. A quantum mechanical state is something in an infinite dimensional Hilbert space. What we typically do is associate with every R, a rotation, a transformation, an action on the states, and that action is associated with some linear operator in the space of acting on the space of states, which I call U of R. There are at least two criteria it must meet so that this operator can be reasonably called a rotation. One is that it should be unitary for every R. Because certainly we don't want the idea of rotating a state, of picking up this ashtray and rotating it to change the probability, the total probability of the ashtray being there. And secondly, we wanted to have the algebraic multiplication structure of rotations. That is to say, given two rotations, U of R1, U of R2, we want this to be U of R1, R2. Actually, wise guys in the audience, or wise gals, I shouldn't be sexist, will say that we only want this to be true up to a phase, but I'll ignore that for the moment. I'm not talking about half-odd integral spins in this lecture. Then we have a reason, at least if we have these, this, by the way, technically is described by saying that the unitary operators U form a representation of the three-dimensional rotation group. Then we can say we know what it means to rotate a state, and once we know what it means to rotate a state, we can go on to investigate whether the dynamics we have defined is invariant under such rotations. Of course, this is not restricted to rotations. Even in non-relativistic quantum mechanics, we also have spatial translations and temporal translations as invariances of the world. And, however, by writing down the momentum operator and the Hamiltonian for our system, we have already told you, if you know the general principles of non-relativistic quantum mechanics, what the unitary operators are that affect spatial translations and temporal translations. Let me just write that down here on the side. The general definition of the momentum operator from non-relativistic quantum mechanics tells us that the operator that makes a spatial translation by a vector A is e to the minus I p dot A. That's the operator which, given a state of the ashtray where the ashtray is here, produces a state of the ashtray where the ashtray is there, where here and there are related by the vector A. Likewise, the Hamiltonian is related to time translations. That's, of course, the famous Schrödinger equation. And we can put the whole thing together in a relativistic form by defining the operator p mu to consist of the Hamiltonian and the momentum, and then say that the space-time translation by a 4-vector A is e to the minus I, that 4-vector P dot 4-vector A, where that's the 4-dimensional inner product. The space part of the, for spatial translations, this reduces to this, and for time translations, it reduces to the appropriate thing involving the Hamiltonian. And I wrote it wrong because there's a minus sign in my metric. It should be plus here. What?
Do you want e to the minus IHT?
No. E to the minus IHT corresponds to a spatial translation. Oh, good heavens. We have to go through that again. Okay. Suppose I have a wave function that corresponds to a state of a system like an atom that does something definite at time 0, turns blue. Okay? The state that corresponds to the same thing translated forward in time by 1 second is a state that turns blue at 1 second. Okay? This is not the state you get by applying e to the minus IH 1 times 1 second to the original wave function. That gives you a state that turned blue at minus 1 second. Okay? It's always this minus sign. Now, now, of course, what we really want to consider for our system, in the first instance, before we start worrying about Lorentz transformations, oh, I should say, for the system under consideration, these objects are already okay. They obey the commutation relations. They all commute with each other, which is right because spatial translations should all commute with each other. And they're all unitary operators because they're exponentials of Hermitian operators. Now let's try and enlarge things for a particular system to include the rotations, which by some flaw in my pedagogy I began discussing before I discussed the translations. I apologize. How we define a unitary operator that affects rotations is rather, damn it, sorry, got ahead of myself. When we consider both the translations and the rotations, we want not just these rules, this representation for the rotations, but representations for the full group. And that means we have additional conditions which we have to impose on our unitary operators that realize rotations, which I will denote as 3 and 4. 3 says that the momentum transforms like a 3 vector, and 4 says that the Hamiltonian is invariant. These are just the infinitesimal forms obtained by differentiation of the statement that rotations commute with time translations, and that rotations and space translations have complicated multiplication rules among themselves. You can get back to these, the appropriate finite forms, just by exponentiating these equations. Now, can we find for this system a rotation operator that satisfies these 4 conditions? By the way, the 4th is what is usually called rotational invariance. Well, the answer is there is an obvious rotation operator that does the job. And that rotation operator is U of R acting on P, simply rotates the vector P. That is to say, if you have a state of a system that corresponds to a single particle with momentum this way, you rotate it and you get a state of a system that corresponds to a single particle with momentum in the rotated direction. Now, I said it's obvious that this obeys the conditions 1 to 4. However, it's not quite obvious, and later for to warm up for Lorentz transformations, which will be a bit more complicated, I should begin the demonstration that this object defined by this equation obeys the conditions 1 to 4. I won't carry it through because once you catch on to the fundamental trick, the rest will indeed be obvious. But I will at least begin it. Before I begin it, though, I was a little confusing, I think, in explaining things from here to here. So maybe people have questions. If so, will they ask them? Questions, please. I encourage questions. I love questions. If I don't get questions, I've finished my material by 3:30 and then I'm very embarrassed. Questions. Lectures are designed to. Yes, sir.
It's not clear to me why this is when you integrate that, you get the finding.
Well, I don't even have to integrate it in this case. Things are simple because everything commutes. I just have to exponentiate it. Okay? And when I exponentiate it, that is to construct, say, for example, U of R adjoint e to the minus I p dot a u of r. Okay? I can imagine expanding this out in a power series. Okay? Whenever I've got a u of r adjoint u of r on a power of p, this equals e to the minus I rp dot a. Okay, is it clear to you how this equation follows from this equation? Which I could just as well write as e to the minus I p dot r inverse a, since the three-dimensional inner product is rotationally invariant and I've applied r inverse to both terms, equals, so thus I have u of r adjoint, u of a, u of r equals u of r inverse a. Okay? Now I multiply by u of r on the left, since u is unitary. That gives me u of a, u of r equals u of r inverse a. Whoops, sorry. Equals u of r inverse a, which you should recognize as the rule for how to turn a product of a rotation and a translation in one order into the product of a rotation and a translation in the other order. Okay, the multiplication rule for how to multiply rotations and translations. Okay, is that clear? I went through it fast, but I could go through it more slowly. This is all you need, because then if you have a product of a bunch of rotations and translations, you shift all the translations over to one side where you know how to multiply them, and all the rotations over to the other side where you know how to multiply them, and then you know what the product is. Now, let's begin by checking the simplest thing, which is unitarity. Once you see how I check unitarity, you'll see how easy it is to check everything else. So I'll just look at 1, and in fact, I'll just look at half of 1. As a preliminary equation, I'll take the adjoint of this equation. Pu of r equals rp, bras instead of kets. Adjoint. I said I was going to take the adjoint, but I didn't write the adjoint. Now let's investigate u of r adjoint to prove that it is 1. It was pretty silly proof because it's sort of obvious from the definition that it's 1, but let's go through it. U of r adjoint. By assumption, the p's are a complete set of orthonormal eigenstates, and they are delta function normalized. So I can write this as u of r integral d cubed p u of r adjoint. Absolutely no question there, I hope. I have just inserted 1 and written it out in a somewhat obscure form. Now I bring the u of r and the u of r adjoint inside the integral sign and use the above formulas. D cubed p rp rp. Now I define p prime equals rp. I observe, since all rotations, proper rotations, have determinant 1, d cubed p equals d cubed p prime. The determinant factor that normally emerges in changing integration variables is 1. Thus I have u of r adjoint equals integral d cubed p prime p prime, which is 1, the desired result. Okay. Likewise, all the other properties follow by a similar sequence of a similar sort of analysis. writing a similar representation for, well, this one is trivial, writing a similar representation for the total momentum enables us to establish this equation, etc. However, there's a key point I want to focus on. The point in the analysis that enabled us to prove the unitarity was this equation. The fact that the integration volume, the measure, as a mathematician would say, that came into our expression for the identity operator was itself rotationally invariant. Now, this gives us a clue on how to define Lorentz transformations. Now, before I say that, let me emphasize the point even further. Suppose we had been extremely dumb and had defined things in a different way by adopting a different normalization convention from this one. Suppose, for example, in setting up my theory, keep this on the board, I were to have defined P, what do I call it? P sub D for dumb. As say 1 over, no, better the other one. 1 plus pz squared, with the z component of p. Perfectly free to do that, of course. This is merely a convention. I can normalize my states any way I want to. These are momentum eigenstates if the original ones are momentum eigenstates. P dumb, of course, would be normalized differently. P prime dumb, P dumb, is 1 plus pz squared delta cubed of p minus p prime. The expression for the identity operator would be different. It would be integral d cubed p, the inverse of what appears here, 1 plus pz squared, p dumb, p dumb. Now, if I had dumbly tried to define a rotation operator by saying u of r on p dumb equals r p dumb, sorry, rp dumb, I would be making a dumb mistake, because this operator, thus fulfilling my notation, because this operator is in fact not even unitary. And the proof of unitarity would break down because this measure, this way of assigning volumes to pieces of p space, is not rotationally invariant. If I tried to go through the proof, I would reach a breakdown at this stage. Now, the question that therefore comes to us in analyzing Lorentz invariance, where we want to do a similar thing, is this a smart or a dumb normalization convention for defining Lorentz transformations? That is to say, is this way of assigning volumes on p space invariant under Lorentz transformations? It's certainly invariant under rotations, but is it invariant under Lorentz transformations? Is this a Lorentz invariant measure? If it's not, then a Lorentz defining what a Lorentz transformation is will be rather complicated, because just as it would be complicated writing down the proper expression for what a rotation does if we insisted on using this dumb normalization convention. The correct expression replacing this false one would have all sorts of factors of 1 over the square root of pz squared on the numerator and the denominator, and it would be hideously ugly. Well, the easy way of figuring out whether our measure d cubed p is a good normalization convention from the viewpoint of making relativity look simple, or a dumb one, is to try and figure out what is a Lorentz invariant way. A little drawing might be helpful. The drawing is only symbolic because I cannot put 4 coordinates on a 2-dimensional blackboard. But at least I have separated space and time. The actual 4 momentum admitted by our particles, as we see from this, lie on a time-like hyperboloid here. This is a hyperboloid, p0 equals omega p, or equivalently, p squared, the four-dimensional square of p, equals mu squared, p0 greater than 0. So we don't get the bottom branch of the hyperbola. What we are really doing is labeling points on this curved surface in 4 space by just their first 3 coordinates. When we write d cubed p, that not only assigns a volume to some area down here, it assigns a volume to the corresponding area up here. We want to assign volumes to these areas in a way that is Lorentz invariant. When we make a Lorentz transformation on the system, shift around this hyperboloid, and a fortiori, therefore, shift around the points down here, we want the volume of a subset of the plane to be unchanged under such transformations. The easy way to construct an invariant way of making a volume is to just put things together that are obviously invariant. The first thing that is obviously invariant is d4p, because all connected Lorentz transformations have determinant 1. That is a nice invariant object, Lorentz invariant object, but it is unfortunately not a particular good one for assigning volumes to three-dimensional surfaces, since a three-dimensional set, since it assigns volume 0 to all of them, being a four-dimensional measure. We will rectify this situation by multiplying it by another obviously Lorentz invariant object, delta of p squared minus mu squared. That's obviously Lorentz invariant because p squared is Lorentz invariant. And that squishes the measure down to just the hyperboloid we're interested in. Still Lorentz invariant. We also don't, this squishes the measure down to both the upper and the undrawn lower hyperboloid. To stick things on the upper hyperboloid only, I'll stick in a theta of p0. And finally, out of sheer perversity, to make these equations look complicated so subsequent equations will look simple, I will stick in an object that is certainly Lorentz invariant, 1 over 2 pi cubed. This defines a way of assigning a volume to any subset of the hyperboloid in a way that is manifestly Lorentz invariant. Is there any question about this in anyone's mind? Now, let's work out what this is. This thing is equal to d4p, well, I'll split it up into space and time parts, d cubed p, I still have the 2 pi cubed, dp naught, delta of p naught squared minus omega p squared, theta of p naught. No question there. I've just separated out the time and the space component. Remember the definition of omega p. By my standard rule of manipulating delta functions, I can write this as a delta function of p naught only. Over 2 pi cubed, dp naught, 1 over 2 omega p, delta of p naught minus omega p. The other 0 of the argument of the delta function I don't bother to write down because that's canceled by the theta function, which vanishes when p naught equals minus omega p. Now I have an integral, a dp naught, and a delta of p naught minus something, and it is a well-known rule that whenever such two expressions come together, they cancel. In doing any integral, we might as well forget about the integration dp naught, because the delta function will guarantee that that will be set equal to 1, and therefore I write this d cubed p over 2 pi cubed 2 omega p. With the understanding that if I have an expression involving p naught, there's always a delta function there that says p naught equals omega p. This is therefore a Lorentz invariant way of assigning measures to subsets of the p-plane, measures in such a way, volumes in such a way that they will be unchanged by Lorentz transformations. Is there any question about the construction of this measure? There are lots of fancier ways of doing it, but this is a quick and dirty way. Yes? The hyperbola represented the momentum states of the particle in p naught p space. P naught is always equal to omega p, or equivalently, 4-dimensional p squared equals mu squared. This is just our equation, h equals omega p. And h is p naught. P naught is the energy. Okay, is that clear? I want to explain things to you, not just shout you down. Is it clear? Yeah. These are the allowable four momenta of our system. A spinless particle of mass, well, in fact, a particle of any spin of mass mu. Thus, the measure that is invariant under Lorentz transformations is not d cubed p. It is this thing. So the answer to our question, is this a smart or a dumb normalization convention, is that it is a dumb normalization convention. We must define other states, differing from this just by a multiplicative factor, so we get a smart normalization convention. It's trivial to define such other states. I will label them by a 4-vector p. But of course, there's just a 3-parameter family of them. P naught will always be omega p. And I will define these states in terms of p by multiplying by the factor 2 pi to the 3/2 square root of 2 omega p. These are relativistically, this is the definition of these states. These are relativistically one u of lambda 2 is u of lambda 1 lambda 2 and u of lambda adjoint p mu u of lambda equals lambda mu nu p nu. That is to say, the 4 momentum transforms like a 4-vector under Lorentz transformations. Well, that's it. Have we done everything? Well, we got a system. We've got its dynamics. We know it's Lorentz invariant. We have a precise definition of Lorentz invariance. We've introduced some Lorentz invariant states, which will obviously be nice when much later in this course when we discuss Lorentz transformation properties of transition amplitudes and decay rates and things like that. But there's something we don't know. We don't know where we are. That is to say, or more properly, we don't know where the system is, because although we have a p operator, we don't have an x operator. For this relativistic particle, we know what it means when we say the particle has momentum such and such, but we don't know what it means when we say the particle is at the origin, or off in the Andromeda Nebula. Nothing I've told you so far has any reference in it whatsoever to where the particle is. Now, this is not the particles we know about in nature in general. If we look at a particle, symbolized by the cigarette lighter, we not only know approximately what its momentum is, we also know approximately what its location is. And therefore, the next part of our task, and the thing that will occupy us in the remainder of this lecture, I may not even have time to finish it in the remainder of this lecture. Oh, I've gotten through that, and I've gotten through that. Maybe I will. Is the question of where is the particle? That is to say, can we construct an X operator? Because in non-relativistic quantum mechanics, what tells us where a particle is the position operator. If the particle is in an eigenstate of a position operator, then its location is its eigenvalue. Now, certainly in none of this which I have described, is there any clue as to what the X operator should be? In particular, none of us have much of an idea about what the Lorentz transformation properties of a position operator should be. Should it be part of a 4-vector? No, though. There's no time operator in non-relativistic quantum mechanics. It's rather baffling. But fortunately, we can write down some general conditions about which I hope all of us can agree. And these general conditions will turn out to uniquely specify an X operator. And then there will be a surprise at the end of the lecture, because once we have uniquely specified this X operator, we'll find out it is totally unsatisfactory. And there will be a physical reason for that. But all of that comes later. I just said that to keep you interested. Now, what conditions do we want about an X operator, a position operator? Well, the conditions I will use will not involve Lorentz invariance at all. They will just involve invariance under rotations, transformation properties under rotations, and space translations. Here is our X operator, X, which we are seeking to find. I will put two conditions on it. One is that if I perform a purely spatial translation on X, it should go into X plus A. This is a statement that if I take some state where the expectation value of the X operator is 0, for example, translate it by A, and look at the expectation value of the X operator in the translated state, it should be A. Certainly, this is a very reasonable condition on any X operator in a theory in which we know what it means to move things by A, such as the theory we have now. The second condition says the same thing for rotations. U of R adjoint, X, U of R, should be the rotated X operator. I.e., if I have a state where the expectation value of the position of the particle is here, and I rotate it, I get a state where the expectation value is in the rotated location. Is there any man or woman in this room who doubts that these are two reasonable conditions to put on an X operator? They're the only conditions I will use. I will not assume, for example, that the components of X commute with each other. I'll deduce that from these two conditions. Now let's go through the deduction. From 1, I deduce 1 prime, which is just another form of 1. E to the I, P dot A, X, E to the minus I, P dot A, equals X plus A. I've just put in the definition of U of A, which we had already. Now I will differentiate this equation with respect, component by component, with respect to A at A equals 0. Thus writing out the components. From this side I get I, Pj, Xi equals the derivative of Ai with respect to Aj, which, as we all know, is delta Ij. Have I got it backwards? If I've got it back, no. Is that right? Yeah? That's the normal Px. I have a minus sign here. Hmm? Oh, right. Okay, good. No, the I is on the just right, and then I switch the X and the P. It's right. These are, in fact, just the usual commutation relations for X and P in non-relativistic quantum mechanics. Now you see a new origin for them, but nevertheless, they should not be unfamiliar objects to you. Now, from this equation, one can deduce something about Xi. Xi is I, d by dpj. This just means the operator at pi. This just means the operator that does differentiation in on the p basis wave functions of our state. That has that commutator, surely. Plus a remainder, Ri. Since I'm not doing relativity, I'm not distinguishing between upper and lower indices, so everything is just an ordinary vector. I certainly can write that. This is just a definition of Ri. And since this thing, we know from non-relativistic quantum mechanics or from direct computation, has the right commutation relations, we deduce that Ri Pj equals 0. Now we know something about our system. We know that the three P's are a complete set of commuting operators. And we know from non-relativistic quantum mechanics that anything that commutes with a complete set of commuting operators is a function of those operators. Therefore, Ri must be some function of the P's. Before I write down what function it is, I will now, for the first and last time, use equation 2, which tells me it must transform under rotations like a three-dimensional vector. And that tells me that it must be of the form pi times some function of p squared. Okay? Any questions? Anyone has any questions? If I've gone too fast, I don't know you. Okay, if I knew you, I would know whether I was going too fast or too slow. Half of the people in this room I do not know. If you have questions, ask questions. Now, any function of this form is, of course, a gradient. Any function of the form p times a function of p squared is the gradient of something with respect to p. So I'll write this as d by dpi of g of p squared, some unknown function, some function of p that's determined by this differential equation, or determined by integrating this thing radially outward. Thus, I have got the complete content of equations 1 and 2. The only possible candidates for an X operator are these. Xi is a normal non-relativistic thing plus something that is determined uniquely in terms of some function of p squared. I'm being sloppy with upper and lowercase p's. I hope you forgive me. This doesn't mean the differential operator. This means, just the derivative of such a function. And that's the whole story. But it's not the whole story because there's something more I can do. The something more I can do is change my definitions of what my p states are by changing the phases. Suppose I change the phases of my p states in the following way. Now let me check to see if I want a plus I or a minus I here. I see I want a minus I. E to the minus I, a g of p squared, times p. I'm certainly free to do that. It doesn't affect a single equation I have written down on the board until now. These are still eigenstates of the momentum with eigenvalue p. They're still eigenstates of the Hamiltonian with eigenvalue square root of p squared plus mu squared. They still are normalized the same way as my p states were originally normalized. I shouldn't say equals, I should say goes into, meaning I make this redefinition. When I make such a definition, a redefinition of states, of course, I change the operators in a corresponding way. In particular, I change xi into e to the minus I g of p squared. For the original xi, which I'll write down, I d by dpi plus d by dpi g of p squared. E, sorry, it's getting hidden underneath the erasers, e to the minus I g of p squared. Are there any questions about that? Plus I on the other side. Thank you. There is not a question, but there is a correction. Now, this is an easy object to compute, the x's in terms of my new set of basis states defined by that. In fact, it's practically the same thing, except I pick up a term by commuting the exponential with the d by dpi. What is that? I d by dpi plus d by dpi g of p squared minus, by putting a differential operator to that function of p squared, d by dpi g of p squared. That's what I get by commuting the factor on the right over to the left, where it will be canceled by this. Well, I hope even those of you who have trouble following the intermediate stages of the argument can now follow this stage, which is I d by dpi. Thus, the unique candidate for the x operator, providing one chooses the phases of the momentum eigenstates appropriately for this system, is nothing more or less than the good old-fashioned x operator of non-relativistic quantum mechanics, the operator which in p space is I d by dpi. Any questions about any stage in the argument? Yes, I see a hand. Sir?
The argument where you go from the commutation relation on the top there to Ri just get
There are used both. There are used two also. In general, it could, of course, be an arbitrary function. Each component of R could be an arbitrary function of the three components of P, but it must be a function of this form if it is to have the right rotation properties. Otherwise, it wouldn't rotate right. It's got to be rotate like a vector. So we found the x operator, and we found it to be unique. We know where the particle is. Or do we? Well, let's do a little thought experiment. If we really have in a relativistic theory a x operator, a well-defined position of a particle, then one of the things we should be able to say about it is that the particle does not travel faster than the speed of light. Okay. This is an experiment which we are now capable of computing the consequences. That was an awkward sentence. We can now compute the consequences of this thought experiment. We can start out with a state, since we know what x is, where a particle is localized sharply at the origin of coordinates. That's a non-normalizable state, but so what? It's just a sample computation. We can allow that state to evolve in time, according to the Schrödinger equation, since we know what the Hamiltonian is, and see if at some later time there is any probability for finding the particle having moved faster than the speed of light. Okay, we have all the equipment. All we have to do is do the computation. Therefore, let's do the computation. We start out with a state psi, which at t equals 0 is localized at the origin. We wish to compute the probability density, probability amplitude, I should say, for the particle to be found at position x at some later time t, which, by the general rules of quantum mechanics, is x e to the minus iht psi. Once we have computed this object, we will then check to see if the particle has traveled faster than the speed of light or not. The computation is pretty easy. The original state psi, well, it's the same old p and x operator of non-relativistic quantum mechanics, so you know what that is. It's d cubed p over 2 pi to the 3/2 p. That's the wave function in momentum space that corresponds to a delta function in position space, as I hope you know. Thus, also useful information, xp is 1 over 2 pi to the 3/2 e to the I p dot x. Something which I hope you also know. Again, from non-relativistic quantum mechanics, because they're the same operators, only the Hamiltonian is novel. Thus, we can do the computation. Psi of x and t equals. Well, we just stick things together. We have a p integral left from the expression for psi, so that gives me an integral d cubed p. We have 2 pi to the 3/2, which is 2 pi cubed. We have the e to the I p dot x from the x on the left. And, of course, we have the Hamiltonian, which is e to the minus I omega p t, acting on the p state. So that's the thing. Doesn't look particularly pretty because omega p, as you remember, is that terrible square root. But at least it's an integral which we might be able to do. Well, let's do it. Part of it is easy. We can go into rotational. I remind you, in fact, I shouldn't do things like that. Omega p is square root of p squared plus mu squared. Part of the integral is pretty easy. We can certainly go to angular coordinates and do the angular part of the integral trivially. This equals, I define r, as usual, to be the magnitude of x. Since I don't want to confuse you with p, the 4 vector, I'll call script p to be the magnitude of the space part of p. The integral then becomes everything over appropriate ranges, which I won't bother to write down. P squared dp, d cosine theta, d phi, that's d cubed p, 2 pi cubed, e to the I, script pr cosine theta, e to the minus I, omega p d. This lecture is going to run 5 minutes over, for which I apologize. Got launched into the subject and I want to finish it. The angular integrals, as usual, are trivial. The phi integral just gives us a factor of 2 pi. The cosine theta integral gives us 1 over IPR. So I get, now putting in the range explicitly, 1 over 4 pi squared I, integral from 0 to infinity, p dp, e 4 pi squared IR, e to the I PR minus e to the minus I PR from the upper and lower ends of the cosine theta integral, e to the minus I square root of p squared plus mu squared t. This is a sort of messy integral full of oscillations. It's rather difficult to tell if it vanishes or doesn't vanish outside the light cone. However, we can simplify it a bit by changing the range of the integral from 0 to infinity to minus infinity to infinity. One over 4 pi squared I, integral from minus infinity to infinity, p dp, e to the I pr, e to the minus I square root of p squared plus mu squared t. The range from minus infinity to 0 gives precisely the second term in the previous expression. Now, we want to investigate this thing for tr greater than t. Remember, the speed of light is 1. So if the particle is traveling faster than the speed of light, which is the thing we want to check about, then the sign of that will be the appearance of non-zero probability amplitude for r greater than t, since it started out at r equals 0 at t equals 0. I dropped an r, thank you. Now for r greater than t, we can write this integral in a somewhat more transparent form by distorting the contour of integration. Let me draw the complex p-plane. Our integrand is, of course, not an analytic function of p. It has a cut when p with a branch point at p squared equals mu squared. And therefore, I have a branch line, which I'll choose to be here, going up the positive real axis, and a branch line, which I'll choose to be here, going down the negative real axis. Our original contour of integration is c. Now, for r greater than t, as we go in the upper half plane, that is to say, we give script p an imaginary part. R is positive, so this is a damped exponential. And p is, well, t is also positive, but that's not particularly relevant. This is an increasing exponential on one side of the cut and a decreasing exponential on the other side of the cut. However, since r is greater than t, the damped exponential is always more damped than the increasing exponential is increasing. And therefore, we can distort the contour to this without any contribution from the big circle at infinity. So we do it. I introduce an integration variable, p equals iz. My integral becomes 1 over 4 pi squared ir integral from mu to infinity minus z dz. That's p dp rewritten. Everywhere along the cut, this is e to the minus zr. On one side of the cut, this is an increasing exponential, and the other side is a decreasing exponential. So this becomes simply the difference between the two sides, which is twice the sinh of square root of z squared minus mu squared t. Any questions? Now, this is bad news, boys and girls, because this integral which we have obtained is an integral of terms, all of which have a definite sign. E to the minus zr along the cut is always positive, z is always positive, and sinh is always positive. Therefore, this is not equal to 0. And therefore, our particle always has a certain non-zero probability amplitude for traveling faster than the speed of light. I hope you understand the meaning, the tremendous and titanic meaning of that statement, even if you have not followed all the manipulations of contours I used to prove it. The manipulation of contours you can go home and do for yourself. It's trivial, straightforward analysis. The fact that the particle ends up traveling faster than the speed of light is a highly non-trivial statement. Now, and here I'm going to run into my 5 minutes extra. Things are not so bad, however, as you would think. Because really it doesn't have much of a probability of traveling faster than the speed of light. It's rather trivial to bound. This integral is impossible to do. That means the answer is a Bessel function. However, it's rather trivial. It's rather trivial to get a bound on the integral by simply taking the sinh and only retaining the increasing exponential part, and then replacing z squared minus mu squared by just square root of z squared minus mu squared by z, which obviously just gives us an overestimate. Therefore, we have 1 over 2 pi squared r integral from mu to infinity, z dz, e to the minus z, r minus t. All I've done is in this twice the sinh I've said is less than the exponential, and the exponential of the square root is less than the exponential of z. Now, this is a trivial integral to do. It does not involve Bessel functions, and since the hour is running late, I will just write down the answer. I hope I did it right last night. I'm always nervous when I just copy things down and don't work them out afresh on the board. Its actual form is not particularly relevant. Remember, we're always working for r greater than t. Now, this is whether I did it right or wrong is irrelevant. And this is irrelevant. The point is we have this tremendously rapid exponential decrease as r gets greater than t. So although it's true that for by purists, if you're a purist, the x operator we have defined is an absolutely rotten, no good, to be rejected x operator. And it doesn't make any sense. It says the particle has a probability for traveling faster than the speed of light, which has never been observed experimentally. If you're a slob, it's not so bad, because the amplitude for finding the particle outside of the forward light cone is rather small. It is exponentially damped. And if we go a few factors of 1 over mu, that is to say a few particle Compton wavelengths, it's down quite a bit. So one way of saying that what we have discovered is that we cannot get a precisely good definition of where the particle is, but if we're only concerned finding out where the particle is to within a few of its own Compton wavelengths, things are not so bad. Is there a physical reason for this? Yeah, and this is what I'm going to end it with. Suppose I attempt to localize a particle in the traditional Gedanken experiment methods of Niels Bohr. In fact, this argument is due to Niels Bohr. I build an impermeable box with movable sides. I put the particle inside it. I turn the crank. Like the Spanish Inquisition, the sides of the box squeeze down. I have localized the particle as sharply as I want. What goes wrong? What has relativity got to do with this? Well, the point is this. If I try and localize the particle within its own Compton wavelength, then not relativity, but our old reliable friend, the uncertainty principle, comes into play and tells us delta p is much greater than mu. It's greater than mu. Roughly, order of magnitudes. There may be a 1/2 in that formula. I can never remember. Now, if delta p is much greater than mu, if the dispersion in p is of order mu, p itself, there must be some probability for finding p itself of order mu. And if p itself is of order mu, we have enough energy in the box to produce pairs. Remember, pair production. Lecture is a cycle. The Rome Ouroboros ends where it began, with pair production. As we squeeze it down more and more, we must have more and more uncertainty and momentum. If we have a large spread in momentum, there must be a probability for having a large energy inside the box. If there's a large energy inside the box, we know there's something inside the box, but we don't know it's a single particle. Could be 3 particles, or 5, or 7. So we can localize something, but what we're localizing is not a single particle. Because of the phenomena of pair production, not only is momentum complementary to position, but particle number is complementary to position. If we make a very precise position measurement, we have a big spread in momentum, and therefore, because pair production takes place, we do not know whether we have how many particles we have. Okay? That's the physical reason for the mathematics on this board. Well, all of this is leading us to the same place. It's leading many of you to decide to drop the course, but it's leading me to devote the next lecture to a discussion of many free particles, which will be the topic. See you then.